A matrix is, what that is it's just a, they call it in the book a rectangular array of numbers. Matrices is the plural of that. Rectangular array of numbers is what a matrix is, and so let me just give you a couple of examples. Yeah, so here we have 2 rows, 3 columns, rectangular array. So it's just numbers grouped together, and they usually put them inside these little square braces, brackets, what do you want to call them. That's what one looks like. It's just a bunch of numbers put together. It doesn't have to be necessarily a rectangle, I guess. This would be a square matrix, but square is just a special rectangle. So anyway, 4, 7, 3, 5. Another one. Let me throw one more here. 2, 4, 3, -1, and 5, 8. Give us another look at a different size there. All right, so one way that matrix, we talk about size of matrix, is we do the number of rows by columns. The rows by columns can tell us the size of this matrix. So we've got 2 rows here and then 3 columns. So this is a 2 by 3 matrix. What's this one?
2 by 2.
2 by 2. And then this one? 3 by 2, yeah. So you kind of get a feel for that. Okay? Now, one thing we're going to do with these matrices is use them in the context of systems. And so let's talk about that. If I have 4x minus 3y equals 11, and then 5x plus 6y equals -10, if I pull off the variables here and then just write the numbers kind of in a matrix form, now you need them in order, x, y, order there for this to really work. And so I'm going to just pull off the variables then. 4, -3, and then write the 11 alongside, and then 5, 6, and -10. I can write that in a matrix form. And a lot of times what you'll see is this little dotted line there just to separate, because the ones on the left there, they have variables associated with it, whereas on the right of that dotted line, it's just a constant. So the dotted line in that scenario just separates the variables and the constants. But this is called an augmented matrix. You see that term? It's what's used for something like this, augmented matrix. And so that's a two equation system in the augmented matrix form. All right. The 1, -4. Start with this. All right. So here back to our three equation systems. X minus 4y plus 3z equals 5. And then minus x plus 3y minus z equals -3. And then 2x minus 4z equals 6. So let's write that as an augmented matrix. what do we got? 1, -4, 3, and then 5. And then the second one would be -1, 3, -1, -3. And then 2, and we don't have a y, but when we write it in the matrix form, we need a placeholder, if you will. So we're going to put a 0 in for y there. And then -4, and then 6. And then throw in a little dotted line there, just to separate those to distinguish its augmented matrix. Okay? All right, now, one special type, or another type of special augmented matrix is one like this. 1, 3, 2, and 0, 1, 7. So that's our augmented matrix, but it's in this special form called row echelon form. This is in row echelon form, and here's why. You can see that the first one starts with 1 in the upper left corner. All right, then the one below it has a 0 below the 1, and then the first one that has a non-zero value, let's put it that way, is also a 1. So the first row starts with a 1, and then the second row, the first non-zero term, has a 1 in it also. Okay, so that's kind of what row echelon form, or how that works. You got kind of 1s along the diagonal, and then zeros. Let me show you another one. A three equation one. 1, 6, 5, 0, 1, 2, 0, 0, 1. Oh. All right. So 1, 6, 5, and then -4, 0, 1, 2, 5, and then 0, 0, 1, and then 7 over there. This is also row echelon form, because notice, like I said, along this kind of diagonal, think of it, we've got the 1s, and then below that diagonal you got zeros. So that's what we're looking for when we say row echelon form. Okay. First one starts with 1, and the ones before the 1s are 0. So that's the idea. Now, what's good about the row echelon form in these augmented matrices is that when you get it in row echelon form, it's real easy to solve the system. Because notice here, what are the equations here? It would be 1x plus 3y equals 2, and then 0x plus 1y equals 7. Well, if I've got it in that form, I've got this thing solved, don't I? Because I've got the y is 7. All I have to do is go back and back substitute. To solve this thing. Y is 7, so I can back substitute. All right, so x plus 3 times 7 equals 2, so x plus 21 equals 2, so x is -19. Yes? So -19, 7 is this solution to the system. Right? So let's do the same with this one. So let's write that back in system form. and then back substitute to solve. All right, so we've got x plus 6y plus 5z equals -4. Had the z in there. Then the second one would be y plus 2z equals 5. And then the third one would be, well, the x and y are 0, so it'd just be z equals 7. So we got one of the variables, but we can back substitute and get the other variables, can't we? Because the second equation now, I've got the z as 7, so that would be y plus 2 times 7 equals 5, so that tells me the value, I get the value for the y. -9?
Yep.
Well, now I have the z and the y, and so can I plug those into the first one? So the y is -9 and the z is 7 there. So I plug those into the first equation. I've got x, what, minus 54 plus 35 equals -4, which is x minus 19 equals -4. So it looks like x is 15. Yeah. You got that? All right. So we've got 15, -9, and 7. That would be the solution to this system or whatever system it's linked to. Okay? Is that all right? Okay.